All right, so any questions? Any issues with the ODP? Straightforward. PA3. Stacks queues. Linked lists. Just point out the head and the tail or the top of the stack, yeah. And put them all on one line, spaces in between, with the right thing on the right side. So there had been a typo in here. It originally, for 211, the README said struct star tnode small. That's a typo, so I changed it to struct tnode star. Struct star tnode will give you a syntax error when you try to compile. So some people caught that. So yeah, make yourself a 3-node tree, root, left value, right value, and assess it. And the test bed, as usual, is temp main-211.0. So by request, I posted a file under /temp called PA3 sample. This is my executable version of PA3. It does not have source code in it. But you can use this if you're not sure what's supposed to happen when I insert a number in stack mode. Well, you can play with it, right? And see what it does. So if you can't remember what something's supposed to do and the description isn't clear and you don't feel like emailing me, you can run this and compare your code to it, right? But you can also just ask. I don't understand what this is supposed to do, so go ahead and ask if you like. And just for you, I got rid of my memory leak so you can val grind this and see what val grind should do. All right, so that's up there on the server, and I posted a note on Canvas accordingly. All right, well, let's take a look at the midterm. So this is posted on Canvas. And possible topics for the midterm. This should be pretty much the major things. But first disclaimer is that anything that we've done up to this point is also fair game. You should know 224 stuff. You should be able to deal with command line arguments, scanf, fgets, things like that, right? Not that I'm going to grill you on those, but you may need to use those things to do what you're doing in here. Same thing with if statements and loops and all of that good sort of stuff. But the stuff sort of specific to 222 that you should definitely feel like you need to be responsible for. So structures, right? The structure statement for defining a structure. So struct, structure name, curly bracket fields, close curly bracket, semicolon. You should have that nailed down. You've been doing it from the beginning of this course and possibly before. Pointers to structures. So we can have a struct node X or we can have a struct node star X. Okay, struct node X, X is actually a struct node. Struct node star X, X is a pointer to a struct node. If it's a pointer to a struct node, it doesn't actually point anywhere until you give X a value. And typically we do that by allocating memory with a malloc statement. And usually if we're pointing to a struct X, we'd want a malloc size of struct X, okay, whatever the structure is. So allocating memory and then accessing fields of a structure. So if we have something like struct node N and struct node star NP for node pointer. So we could say N dot data to access that field. But for NP, if we want to access a field, we can say NP arrow data. And that's the same thing as dereferencing NP, so it's actually a struct node and then using the dot. Right, so this is equivalent to, but don't do that, do this. So that's how we dereference fields. And then arrays of structures, I don't know why I put that on there, but you can make an array of structures. So just like any other type of variable. All right, linked list will definitely be on the midterm. Okay, we've got 2 programming assignments down on linked lists. So you should understand the idea of a sentinel node. Okay, it's the node in the beginning of the list that doesn't actually represent part of your data. It's just a holder so that you always have something in the list. Algorithms for searching a list: start at the first data node and just follow the links until you find your thing or you run out of nodes. Traversing, which is like moving from the beginning of the list to the end, but typically printing the data values along the way. Inserting and deleting, right? So being able to adjust pointers. I will almost certainly give you a question where I'm asking you to insert or delete into a linked list, but I'm not going to let you do it by writing down the code you wrote for PA2. Okay? I'm going to want you to manipulate these nodes and the fields inside the nodes by hand, more like what you've done in the ODPs. Okay, so you want to understand the algorithms for inserting and deleting, how the pointers get adjusted in the nodes. Doubly linked list, just the basic concept. Each node has a forward pointer and a backward pointer. Okay, whereas a regular linked list, you only have forward pointers. Order of complexity of list operations and array operations and lists versus arrays. So here's what I think you should know about order of complexity. So basically, our operations are insert, delete, and search. And we have an unordered array. So we don't care about the order of the things in this array. And in general, to insert into that, all we have to do is just take the thing we're inserting and add it to the end of the array. And then note that we have one more thing in the array. So this is going to be order 1. It takes a fixed amount of time no matter how big the array is. If the array has 1,000,000 entries in it, and we just want to add one more entry, we just go to the end location of the array and we store it at that index. And the fact that there's 1,000,000 things before it doesn't change that time. To delete an entry, well, if we have something like a valid flag and we want to delete this particular entry from the array, we could just clear that valid flag, right? But in general, when you delete something from the middle of an array, we want to shove everything up to sort of fill up the space. So this is probably going to be order n, meaning that if your array has size n, it takes you roughly n operations. And search is definitely order n, because there's no order to the data in the array, so the only choice we have in looking for something is to check every entry in the array to see if that's the thing we're looking for. So that's order n. But when we have an ordered array, sorted, our search time drops to log n. That's where we're playing high-low. We can cut this array in half each time that we do a search, each time we do a comparison. And after log n of these comparisons, the array we'll be searching will be a single element. And it's either our number or it's not. So search is very efficient, but to insert into a sorted array, that's going to be order n. And to delete is going to be order n. Because if we want to insert in the middle, we've got no choice but to take everything below that insert point and move it down one spot. And that's an order n operations. We have to move n things to a different place in the array. So with a linked list, and we're assuming that this is a linked list where the data is ordered, Otherwise, it's basically like an array. A linked list, if we want to insert, the actual act of adding another node into the array is order 1. And the actual act of removing a node from the array is order 1. But to actually find where we want to insert is going to be order n. So when we were inserting or deleting, we started at the first node, we followed through until we found the right spot in the array. And then it's a very inexpensive operation, order 1. But it's generally order n to find where to act. And the search is absolutely dreadful. It's order n, because we can't play high-low, so it's just like an array. The sort doesn't save us any time. And then, not on exam, but since we're making this nice table anyway, a binary search tree, this is going to bring us back to log n for searching. That's the whole point. And our insert and delete will also be log n. So we get back the nice search time of an ordered array, and the insert and delete go from n down to log n, which is totally manageable. Means if you have a billion things in your tree, it only takes you 30 operations to insert, to delete, and to search, which isn't bad. So that's what we're doing now, but not on the exam. All right, so that's order of complexity of list operations and array operations. And then, so you've been working with these things throughout, right? So star is used to take the thing pointed to by a variable. Ampersand gives you the address of a variable. And period accesses a field in a structure, and arrow accesses a field in the thing pointed to by a pointer, right? The structure pointed to by something. All right, pass by value versus pass by reference. This is a concept that you want to keep working on. Basically, in C, whenever we call a function, whatever arguments we pass a copy of those. We pass the value. Okay, we don't actually pass the variable itself, which means that a function has no way of changing the thing that we pass to it. Okay, that's pass by value. And that's always what C does. And when we pass something like ampersand x, the address of x, that's still passed by value. The function cannot change the value of ampersand x. Okay? But if it turns out that value that we passed is the address of x, that function can absolutely change x, because it knows its address now. Okay, but it's not because we're passing x by reference. It's because we're passing the address of x by value. But we consider this passing x by reference, basically. We're passing the location of x. So pass by reference means you pass the address of a variable. Pass by value just means you pass the value of it. If it's a number, you just pass that integer to your function. Okay, so that's a conceptual thing. Malloc and free. So malloc, we know, is how you allocate memory. You tell it how many bytes you want. Generally, you get that number of bytes by using size of. So malloc size of whatever it is, int, double, struct such and such. And it will return either the address of a block of memory or null if it's out of memory. And then free releases the memory that you previously allocated with malloc. You can only free something that you malloc. If you free an arbitrary address, you'll get complaints. So you malloc, use your memory, and when you're done, you free. And then valgrind is the tool that we've been using to check for whether or not we free everything that we malloc, and also to make sure that the blocks we're mallocing are being used correctly. So if we malloc a block that's this big and we try to access something down here, valgrind will give us a warning. Okay, or if we try to free something that we didn't malloc, it'll notice that. All right, GDB, make sure you understand the basics of GDB. So what it is, it's a debugger. How do you compile a program? Put in the -G switch. Okay, if you compile in parts -C and then -O, you need the -G switch in both of those compiles. And then you execute your program with GDB by saying GDB space program name, the executable. You can set up breakpoints, so set break. You can set up watch points, set watch. You can list your code. You can print the values of variables with P. You can examine memory with an X. You get the whole thing started with the start command. And then after you set up your breakpoints to do whatever you want, you can either say continue, which says run until we hit a breakpoint, a watch point, an error, or we finish. Or you can say next, which says go down to the next line of my program. Or you can say step, which says go down to the next C instruction. And if you have a function call, it'll go inside the function and come back to your attention. So step is a step into, next is a step over. And along the way, you can use P to print the value of the variables. You can use X to examine memory. And that's really it for GDB. That's pretty much enough to do everything that we've been doing in the debugger. There's a million other things you can do in GDB, but that's a good subset that should make you pretty efficient with working inside that environment. Makefiles, you want to understand makefiles. You're doing makefiles for every PA in here, right? So you should be getting good with these. These things are not the focus of this course, so they won't be the focus of the exam, but there could be a question related to a makefile or GDB or something like that. So just kind of brush up on those. You understand what you're supposed to understand already. Abstract data types, so this is another conceptual thing. So when you have a linked list, it could be implemented in an array. It could be implemented with dynamic memory. It could have a sentinel. It might not have a sentinel. Your structure might have data followed by next, or it could have next followed by data. Or it could have pointers going backwards to help you move backwards and clean up your insert and delete code, right? Those are all implementation details. As an abstract data type, a list is just this thing that you can say, insert this into the list, search for that, delete this, initialize the list, print the elements of the list, right? Those operations are independent of how the list is implemented. So an abstract data type is a view of a data type from the user perspective, not from the programmer's perspective who's implementing that data type. Okay, so we have this nice clean line here usually between user and implementation. So that's a conceptual thing. Stacks, so basic operations, push and pop, and maybe initialize. Stacks are last in, first out, so the last thing that you push is the first thing that you pop. Underflow happens if you try to pop from an empty stack. Overflow happens if you try to push into a full stack. And two ways to implement stacks that we talked about. One using arrays. So we have an array, we have a stack pointer variable, and that tells you either where you're going to push next or where you're going to pop next or something, right? And we can also implement with lists, that's PA3. So the version of PA3, we have a list and we insert at the beginning to pop, and to push, and we remove from the beginning to pop. And then queues, the same thing, except queues have two ends. There's a head and a tail. And make sure you know which is which. Okay, we insert at the tail, we remove from the head. So think of a line. Think of the front of the line and the back of the line. You never cut into the front of the line or you get in trouble. When you show up at the movie theater and you want to buy your ticket, you go to the back of the line and you wait till you get to the front of the line. Okay, the back is the tail, the front is the head. And queues are FIFO, so the first thing in the queue will be the first thing out. The last thing in the queue will be the last thing out. So basic operations, insert at the tail, remove from the head. Full queue means you can't insert anything more, and empty queue means there's nothing left to remove. And we had two ways to implement these. One using an array, and for that we needed a pair of pointers, head and tail. And when you insert, you move the tail, and when you move the head. And we had this funny business because these things are moving. that when you get to the end of the array, you want to be able to wrap back to the beginning. And you need to make sure that you don't run into each other, which is what happens when your queue is full. So that's the idea of a circular array. The other implementation is with lists. And so you can just agree to insert at one end of the list and remove from the other end of the list, and there you've got a queue. Okay, you're definitely responsible for stacks and queue implementations with lists. Okay, that's PA3. You'll possibly be pretty close, if not completely done with PA3 by Monday, which is the exam. So list implementation should be pretty comfortable. I will hold you responsible for array implementations of stacks on the midterm. You'll probably have a question on that. I will not hold you responsible for array implementation of queues on the midterm. Okay, I might on the final. But queues, just worry about lists. Stacks, make sure you know how to do it with lists and with arrays. Okay, and if I ask you stacks with arrays, I'll give you code to work with. So make sure you've thought about that. And that's pretty much it for topics. Okay, really the major topics that are new are linked lists, stacks, and queues. And then stuff that we've used along the way, malloc and valgrind and things like that. So things you might find yourself doing on the midterm, writing code to manipulate pieces of a structure, to work with pointers, to dereference fields and things like that. So the stuff that you've put into your other programming assignments. Looking at code and analyzing it, figuring out what it does. Modifying code, adding something to it, changing something about its behavior. Okay, we're talking about small pieces of code here, not like 15 pages of C. Performance of algorithms, so right, insert, delete, and search for arrays and lists. Understanding and being able to manipulate lists and stacks and queues. So I could give you a list and I could show you some code and ask you to draw a new list that results from that. I could show you an empty queue and give you some inserts and removes and ask you to show me what's happening to the queue after each of those. Or I could do that for a stack. So make sure you're comfortable with those operations. And then conceptual questions, GDB, valgrind, make files, whatever else. Short answer, fill in the blank, maybe multiple choice. So most of the points will be programming, but there'll be some shorter stuff also. And maybe half the points will be programming. I haven't weighed it out. I'm shooting for 50 minutes. I will try very hard to keep it doable in 50 minutes. But look over the exam, pace yourself. If you finish early, go back and recheck your stuff. So shouldn't be any big surprises in it. All right, so that's posted on Canvas, and midterm is Monday. So 4 pages double-sided, 8 pages single-sided. Tons of notes, man. But write your notes carefully. Don't just shrink down all the code you've written. And I'm going to be very careful in writing my questions to make sure that you can't just take your delete code from PA2 and put that down and get credit for it on the exam, right? So I'm not going to ask you to reproduce code that you've already done. But the things that you understand in writing that delete code, right, that's the stuff that I'll be asking you to use for these questions. All right, other questions? All right. I know we did traversal. Did we do search and insert on trees? I know we did search. Did we do insert? We were returning the root of the tree after insert. Okay. I thought we did. So here's what I want to do. I want to look at this recursion business a little more closely. So here's some sample code for traversing a binary search tree. So our function is called traverse. We pass it a pointer to the root of the tree. This is our standard node. It's got data left and right. And if the root is null, we don't have to do anything. That's our base case. There's nothing to print. Otherwise, we want to traverse the entire left side of the tree in left node, right order, printing out the data as we visit the nodes. And then we're done with the left side. We want to print out the root data. And then we want to traverse the entire right side. And we've said that this code will do that, right? But it's recursive. Traverse is calling traverse. So it's a little weird. So what I want to do is go through an exercise of actually seeing what happens when we call traverse. And let's see if we can gain some insight into how this whole recursion business is working. So let's suppose we've already built a tree. And our tree is going to, I don't know what it's going to look like. There's a tree. It'd be nice if we could write statements like this in C. So root's a struct node star, and this is what it actually looks at. Root is technically the address of this node 20. Okay, but 20 has pointers on the left and the right that point to these things. So that's what root looks like. It's basically a tree. So this is our main program. And we're going to say traverse root. We're just going to call our traversal code once. And I want to see what exactly that does. So when we say call traverse, we create what's called a call frame. It's a kind of completely new context in which this call to traverse is being executed. So I'm going to say this is call frame 1, page 1 of this, and it was called from main. And traverse was called with root being the following tree: 20, 10, 5, 12, 30, 40, 35. That's the argument we passed to traverse. So let's see what traverse does. The first thing it does is it says, is root equal to null? And it's not. Root is actually the address of this node containing a 20, so it's not null. So it doesn't do a return. So now it says, traverse root arrow left. It's making a call to traverse. And what it's passing it is this tree right here, 10, 5, 12. So we're making a new call to traverse. This was called from call frame 1, and the argument that was passed was this. So let's see what happens. It checks to see, is the root equal to null? No, the root's the address of node 10, so no return. Traverse root arrow left. It's making another call to traverse. So we start a new call frame. This is page 3, called from page 2, and we're passing root arrow left. Well, this is root. Root arrow left is just a single node with a value of 5. Bless you. So what does this function do? It says, is the root null? No. Let's traverse root arrow left. Well, remember, the left child here is null, right? We don't show it, but root arrow left will be null. So this makes a call to traverse. This is our 4th call frame. It was called from page 3, and our root is null. So the first thing it does, it says, is root equal to null? Yes, it is. It's going to return. All right, we return back to where we were. This was frame 3. So we come back here to frame 3. We just finished this call to traverse. So now it says print root arrow data. So let me keep track of our output up here. Root arrow data is a 5. So our program is going to print a 5. And that's the end of the print. And now it's going to say traverse root arrow right. Root arrow right is null. So we make a new call frame called from page 3 with root equal to null. Is root equal to null? Yes, so we return to page 3, and now we're done with traverse root arrow right. So this code traverse is finished. It returns. Where does it return? It returns to page 2. We're popping our stack. So we popped the stack. We go back to the previous page. This was page 2. What have we done? We've completed this line of code, traverse root arrow left. Now we execute this line of code, print root arrow data. That's a 10. That's done. Now we say traverse root arrow right. Well, what is root arrow right? It's a node containing a 12. So this is call frame 6. It's called from page 2, and we're passing it a root which looks like this. Is the root null no, traverse root arrow left. And this will look exactly like this other page. So this would be page 7, called from 2. We pass root arrow left, which is null. If root is null, return. It'll come back here. That finishes traverse root arrow left. Now we print root arrow data, which is 12. And then we traverse root arrow right, which is also null. So we'll make another call frame. Root is null. Is root null? Yes, we return. And now we finish traverse root arrow right. So this call to traverse returns. Where was this called from? It was called from page 2. Which line of code was it? It was this one. We were traversing root arrow right. So that's finished. And now this call to traverse returns. And it returns to page 1, where we were doing traverse root arrow left. So we have finished traverse root arrow left. And now we say print root arrow data. That's a 12. So print the 20. Root arrow data is done. And now we say traverse root arrow right, which is whatever page we're up to. I don't know what it is. Let's just call it 8. And this is called from page 1, and we're passing root arrow right, which is 30, 40, 50. And we just keep going. Getting the idea? So is this null? No. This will say traverse root arrow left, which will be null. So it'll make another call to traverse with null as an argument. That will return right away. And then we'll print root arrow data, which is 30. And then we'll call traverse on this 40, 50. So here's frame 9, called from page 8. Here's the tree we're passing. Is it null? No. Traverse root arrow left. So that'll make one more call from page 9, where we pass it root arrow left, which is 50. Is that null? No. So it'll traverse root arrow left, which will be null, and we'll come back right away. And then we'll print root arrow data, which is 50. And then we'll traverse root arrow right, which will make another call to traverse. The argument will be null. It'll come back right away. And now this is done. It'll go back to where it was called from, which was page 9. And so it's completed. Traverse root arrow left. Now it's going to, ooh, we did something wrong. Yeah, I think that should be 35 too. I could have ripped the universe in half there. Okay, now we're going to print root arrow data, which is 40. And then we're going to traverse root arrow right, which is null. So we make another call. Root is null, it comes back right away, and we're done. This traverse is finished. Okay, we're going to return, which means we're going to pop the stack. This value of root goes away, and now we're back to call frame 8, where this was our root, and we just finished traverse root arrow right. That's done. We're going to return, pop the stack, and now we're back to this call frame where we're doing traverse root arrow right. That's done. So we return, and we were called from main, so we go back to main, and now this call to traverse is finished. And this is what's been printed. So that's how it happens, right? It's a lot. And if we look at this and conceptually say, we're traversing the left subtree, we're printing the root, we're traversing the right subtree, and if there's nothing in the tree at all, we don't do anything, right? And if we think that's what traverse does, we can convince ourselves that this traverse is doing the right thing, as long as these are doing the right thing. And when we're thinking about recursive code, when we're writing recursive routines, when we're looking at our code trying to find the problem, this is really the level we want to be at. Okay, you don't really want to be doing this. Okay, it's good to go through once or twice, and it's good to think about in the back of your head, but it's not really practical for debugging. Because if your code's printing the wrong thing and you start trying to see who called who, probably it's going to take you down a big, deep rabbit hole. Okay? And maybe that's what you've got to do, at least the first few times that you're doing this. But at some point, you get to a point where you actually think of this as calling itself recursively, and you just think of this not as going through all this, but doing some function, right? So my goal here is to do some function. I can accomplish that by doing this sub-function, and then this action, and then this sub-function. And ultimately, that's how we're thinking about recursion.
Is it anything faster to have that if statement that checks root left and root right if it's null?
Sure. So we could say if root arrow left is not null, then traverse it. And we'd save one level of recursion.
Is that like significant, or is it's not a big deal? Or?
It will probably significantly cut down the number of calls to traverse. Because every time that we get to a leaf node, it's checking both, and it's just calling traverse to do one line of if and then come back right away. But a lot of times with recursive code, we're not really thinking about performance. I mean, we are, because performance tends to be worse for recursion in a lot of cases. But the benefit of clarity and succinctness can outweigh the cost of performance. So it's trade-offs. But yeah, nothing wrong with doing that. And it's good to be able to do it both ways, I think. All right, so here's our tree. Let's do an insertion. So what do we want to insert into here? Let's insert an 11. And remember, when we insert, we actually say something like root equals insert root, comma, value. And we allow insert to return the root of the new tree that has our data inserted into it. So here's a sketch of some insert code. So we pass a root and a number, and we return a struct node star. And if our root is null, if there's nothing in the tree to begin with, we simply allocate a node. This is an equals sign. We simply allocate a struct node We set its data equal to our number, we set its children to be null, and we return the address of that node. So if we have a totally empty tree, and we say something like root equals insert root comma 11, root would be null. This would create a node, set its data value equal to 11, and return the address of that, and then root would be equal to that address. So it'll point to our root node. But let's see what happens if we already have a tree that root is pointing to, and we try to insert something like an 11. And this has a totally different feel from traversal. It's actually a lot more direct. So let's start off with page 1. It's called from main. Our number we're inserting is 11, and our tree looks like this. All right, so we make a struct node star temp. Temp has nothing particular in it right now. We check to see if root is equal to null. Well, it's not. Root is the address of this node 20, so none of this stuff happens. So now we say if number is bigger than root arrow data, and our number is 11, root arrow data is 20, it's not bigger than 20, so we don't bother doing this if statement. So we come down here to this case, which says insert our number into the left subtree, set temp equal to the return value, set root left equal to temp, and return root. All right, so how does this work? So we're going to call insert, and the root that we're going to pass it is this left subtree. So here's a call frame. This is page 2, called from frame 1. Our number is 11, because we're still passing num. But our first argument, the root, is the left subtree of this, so it's this smaller tree, 10, 5, 12. All right, is root null? No, so we don't do that. Is our number bigger than root data? Yes. So we're going to go ahead and we're going to say insert number into root arrow right. So we're going to make another call to insert. So this is frame 3, called from frame 2. Number is 11. The first argument is root arrow right. That's this tree. That's just a 12. So if root is null, no. If root num is bigger than root data, 11 is not bigger than 12, so we don't do this. So now we say insert our number into root arrow left. So we make one more call to insert. This is called from frame 3. Our number is 11. The root is root arrow left, which is null. So now the code starts to execute. If root equals null, which it does, so it's going to say temp equals some new node, right? And we set the data value equal to num, which is 11, and these are null. So this is just a tree consisting of a single root, 11. And we return that as the function value of insert. So we return, we come back to where we were called from, which was frame 3, and we were doing this instruction temp equals insert. Well, since this thing returned a node containing 11, this sets temp equal to just this node containing 11. So we finish that call, and then we say root arrow left equals temp. Here's what root looks like. We set its left node to be temp, which is just an 11. And then we return root. So this call to insert is going to return this tree. Well, where were we called? We were called from frame 2, which was this statement right here. Insert is returning this tree 12, 11, and this is setting temp equal to that, so temp looks like this. So that completes that call. And now we say root arrow right equals temp. Well, here's root. We want its right child to be this tree. So this is a 12 and an 11. That's how this tree looks now. And then we say return root. So this is a return value from this call to insert. It was called from page 1. So temp is equal to the return value. So temp is this 10, 5, 12, 11. And that completes that. Now we set root arrow left equal to temp. Well, this is root arrow left down here, and we want it to be a tree containing 10, 5, 12, and 11. So that's what root now points to. And then we say return root. This is the return value from this call to insert, and it was called from main. Well, in main, we said root equals whatever the return value is. So now root is going to be set equal to this thing, which is just this. And so that one call to insert, root 11, gave us back a tree that looks like that. And that's a little less hairy than the traversal code, right? Because when we're traversing, we're kind of like branching out, and each time that we go down one level, we start going off into more different directions. Insert is very direct. We start at the root and we go bang, 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 and it takes us right to where we need to insert, and then we kind of pop back up along that path. And as soon as we went to the left of 20, we knew we were never going to touch these nodes, right? There could be a million nodes over here. They're not going to factor into any of this. All these other calls to insert are going to have subtrees from the left. So insertion, even though the code is a little more complex, right, because we're passing back a struct node star and we're adjusting the tree, the level of calling itself is much less in general. All right, so that's a view of what recursion kind of looks like. And like I say, it can be really maddening to try to sort of wrap your brain around that. But inevitably, you try to wrap your brain around it to some degree. And when that works, great. When it really doesn't work and it just feels like you're going in circles, don't worry about it, right? Come back to it a little later. Write some code, sleep on it, come back to it, and it will start to click, sometimes in little pieces here and there. And over time, it'll make more and more sense. And eventually, like I say, one day you'll wake up, and this will be, you know, kind of the most obvious thing in the world, and you won't be able to imagine doing an insert any other way. And that's a really good place to be, because it's such a powerful technique for writing code and for implementing algorithms. So we're heading there, and working on trees will be a good part of going in that direction. All right, almost perfect timing for a break. So let's take a 5-minute break, and then we'll come back and we'll talk about deleting from trees, which is another source of fun and entertainment.